All right, so we mentioned that displacement is important because that's an indication of how much energy is stored in the spring potential energy. And velocity is also very important because it is an indication of the amount of kinetic energy is stored in the spring block system. So let's see, how do we calculate? How do we find out spring potential energy and kinetic energy based on this information? For a simple harmonic motion, when the displacement can be described by this expression, when the velocity can be found by this expression, what is the kinetic energy? Let's start with the kinetic energy. How do you calculate kinetic energy? So that's your capital K, kinetic energy. 1/2 mv squared. So is kinetic energy a constant? Is it a constant? If it's not a constant, why is it not a constant? Because velocity changes with time. So your kinetic energy now is not a constant. It actually changes with time. So your K to be rigorous, you would say K of t, because now it's a function of time. Okay, and that's equal to 1/2 mass of the block, which is not changing with time, but you have the velocity, which changes with time, and that velocity you have to square it. So you have kinetic energy, that's 1/2 mv squared. So what we're going to do is that we're going to replace this v with that expression. So I'm going to square the whole thing here. So what we have here is that we have 1/2 mass omega squared and your xm squared, and then we have sine squared. Now I'm just going to use my theta here to indicate that's omega t plus b, so I don't have to write out the whole thing. So it's just sine theta squared, okay? So this is expression for kinetic energy, and you can see that it depends, it's equal to 1/2 mass omega squared xm squared sine omega t plus b squared. Okay, seems rather lengthy, but you'll find that after you go through some steps, it is not. Now let's look at potential energy. Potential energy, because displacement is a function of time, so potential energy is also a function of time. How do we find out the spring potential energy? 1/2 kx squared. So you have your 1/2, and you have your spring constant, and you have your x squared, but it is x of t squared, right? So what I'm going to do is I'm going to utilize this expression, square it, and copy them down. So you have 1/2, you have your k, you have your xm squared, and then cosine theta squared. So again, I'm going to use the theta in place of omega t plus v. All right. So what is the total energy of the system? What is total energy of the system? How do you find the total energy of the system? Huh? Mechanical energy, right? So mechanical energy is equal to, and by the way, so is mechanical energy a function of time? The total energy of the system, is it constant or a function of time? Huh? The total energy of the system. Yes? Why is it constant? Conservation of energy, right? For an isolated system, the total energy of the system should not change if there's no external force acting on it. This is an isolated system. There's no external force to act on it, so which means that total energy of the system will not change. The total energy will not change, so your mechanical energy is actually a constant, despite the fact that kinetic energy and potential energy are changing with time, but the sum of them will actually give you a constant. Okay, so your mechanical energy is the sum of potential and kinetic, so we just add them together. In the book, it does not say that it's K of t or U of t, but just to make just to make you aware that they are function time, so I'll actually include that L of t. Okay, so when you add this together, let's see how we just pretty much just add them together. So it's 1/2 mass omega squared xm squared sine squared, and then plus 1/2 k xm squared, and then cosine squared. Whew. Didn't I say it should be a constant? but it looks very complicated. And you have that theta. Theta is a function of time. Am I contradicting myself? Yes? Okay, but can we do this? Can we just add them together in the present form? How do I rearrange it? Because in order to utilize the identity that this plus this is equal to 1, the condition is that the coefficient in front of those two has to be the same. The coefficient in front of them, are they the same? At the moment, it appears they are not the same, right? So, that's where this equation comes in. Let's see if we can actually work on this equation to see if we can achieve the goal that the coefficient in front of this sine so form actually all the same. Let's see if we can do that. So you have your omega square. We have omega square, so how about we start with this one? So you have your omega square. Omega square is equal to k over m. So if you replace this with k over m, then what we have is that your m just cancels. So what do we have after you do the replacement? So you have your 1/2, your m just cancels, so you have your k, and then you have your xm squared, and then sine squared. That's your first term. The second term, you have 1/2 kxm squared, and then cosine squared. All right, so are we getting somewhere? We are getting somewhere, right? Because now we found that the coefficient in front of the sine and cosine, they are the same. If they are the same, we can actually just use this to add them together. So when we add them together, what do we have? What do we have? When you add them together? Huh? What do we have? Yes? That will be 1/2 kxm squared, right? So from this complicated lengthy expression, we arrive at this simple expression. Your mechanical energy is just equal to 1/2 kxm squared. Okay? So this is when all the energy has been restored. All the energy has turned into spring potential energy, because there's no kinetic energy involved. It's just a spring potential energy. Okay? Likewise, we can do substitution the other way. Let's say your K is equal to omega times n. So you can actually Vm omega. Yeah, we can do that. So we can use K that's equal to omega squared times n and see what we get here. So you have 1/2 your K, just omega squared, and then you have your m, and then you have your xm squared. What do we have here? So you have 1/2 mass. What is omega times xm? Omega times xm, that gives you amplitude what? Velocity, exactly. That's your Vm squared. So this is the situations when there's no spring potential energy, all the energy has been stored in the form of kinetic energy. Okay? You do not have a situations that you have the energy that's 1/2 kxn squared plus 1/2 mvm squared, because it's either me or no. All right, either this or that. You cannot have the combined of the both amplitudes. You could have partial kinetic energy, partial potential spring potential energy, but you cannot have all the energy that's in kinetic and spring potential adding together. Okay, so in other words, what we have here is that your mechanical energy, which is a constant, is equal to 1/2 kxm squared is equal to 1/2 m Vn squared, and that's equal to kinetic energy plus potential energy when that is not reaching the maximum. Okay, so we have some energy. For example, let's say the system has 11 joules. You can have the 11 joule as, and then there might be situations that spring, the kinetic energy has 5 joules and spring potential energy has 6 joules. So when you add them together, that gives you 11. Or you can have situations that this has 4 and this has 7. Or you can have situations that, so this is one scenario, or you can have K that's 11. If K is 11, which means that U is 0, and vice versa. You cannot have 11, 11 simultaneously. You can 11, 0, or 0, 11, or the sum of those two. Okay? All right. Any questions so far? So this describes the conservation of energy. So again, conservation energy of this chapter is very important concept that you're going to utilize again and again. Your mechanical energy is equal to this or that, and then when you do problems, you would for a lot of time you will use the from the conservation of energy to approach the problems. Yes. I'm just saying that if mechanical energy is, you have a mechanical energy that has 11 joules. You can have a scenario that you have kinetic energy that's 5 joules and potential energy that's 6 joules, or you can have kinetic energy that's 11 joules. If kinetic energy is 11 joules, then you have 0 joules for potential and vice versa.
So you can have some combination of...
You can have combination, but you cannot exceed the maximum. That's 11. Yeah. Okay? Any other questions? All right. Okay, so this is described the simple harmonic motion, and you did that in the lab. So you have the spring, you set it up, and then it oscillates. We also might have a situations that it is actually not moving in the up and down, or right and backward and forward, but actually is set of motion that's in torsion. I don't know if you had a chance to observe it in the lab. Because in the past, when students did the experiment, when they pull it down and when it oscillates, in addition to oscillate, the spring, where it's attached to the mass holder, is actually doing this as well. Did you notice that when you did the experiment? Okay, so maybe not this, but there's students, when they probably depending on how you say that, and then there's actually doing the torsion, that kind of oscillation, and that's all oscillations, is just like rotating. So instead of going this direction, that direction is actually rotating like that. So this kind of a motion, we call that, it is still a simple harmonic motion, but it is torsion. Okay, so I just want to briefly mention that to utilize, because torsion is rotational simple harmonic motion. So to utilize what you have learned, and remember, linear motion and rotation, they bears a one-on-one correspondence. So let's say in linear motion, you have simple harmonic motion that's like this. The spring force acting on the block is equal to spring constant times the displacement, right? So when you have torsion, when something that rotates about a point, it also, and then executing a simple harmonic motion, we know that there is a torque acting on the object, and there's an angular displacement as well. So what kind of expression would you expect? Or what is the angular form for Hooke's law? This is the Hooke's law in linear form. What would be the expression for Hooke's law in rotational form? So your force is equivalent to torque, exactly. So you have your torque. Now it's a function of time, all right? And that's equal to, instead of the spring constant, there's also what we call the constants. We call that kappa, and they actually look very similar to each other. So let's say this is kappa, the Greek letter. Now displacement. What is equivalent displacement in angular form? The angular displacement. Theta, exactly. So now, as we mentioned, when when it is in simple harmonic motion, it is a function of time. So your theta is also a function of time. It describes how to rotate back and forth and back and forth. Okay. So this is basically what I want to say about the angular simple harmonic motion that sometimes you observe, and then the use of that is actually quite straightforward, because you just simply once you identify the one-on-one correspondence, this is torque, and this is force, and this is a constant, and this is displacement, and this is angular displacement. Okay, that's just for your information. All right, so the other thing that another example for simple harmonic motion is that we can have a pendulum, and then we just let the pendulum oscillate. For example, let's say you have a thing, huh? Oh, sorry.
I have a question about the torque thing.
Yeah.
For that theta, it's not the same as the other theta, right?
That is the same theta.
Oh, so it's the WT plus that little.
Oh, you mean that theta? Oh, this is the angle, but this is also the angle, but then now this angle actually is a function of time.
Okay, so like that little theta is not the same as the WT plus that.
In a way, no. That WT plus V, that is what we call phase.
Okay.
And this is like this is the display. This is like the position, but now it's angular position.
Okay.
Yeah. So this angular position. All right, so for pendulum, let's say we have a simple pendulum. How does it work? And what do we use for the simple pendulum? So, okay. So let's say you have a string. On one end of the string that is tied to a bulb. Okay, so let's say the arrangement is like this. So you have, let's say, some sort of fixture. And you have so this is your rotation axis. And this is a string that you have a bulb. So the bulb, because of its gravity, is going to oscillate like that. That we all know, right? And this is how I forgot that word. When somebody, they're trying to what's that word that you're trying to, huh?
Like hypnotizing?
Yeah, hypnotizing. Yeah, they're trying to hypnotize you, and you look at that. Ooh, yeah. All right. So let's study how this simple pendulum works. So you have a string that's massless, okay, with an negligible mass, and this bulb has a mass m. So we know that there should be a tension. So if we draw a free body diagram of this ball, how many forces acting on this ball? Let's say this is our reference point. How many forces acting on this? There will be two. One is tension, that should be in this direction, and the other one is mg, gravity, right? So that's your gravity, that's your mg. Okay, so let's say so let me draw a reference line here. So let's say this is your angle theta. It is an angle theta in reference to the vertical line. So we can actually see that your mg, so that's it, we can resolve your mg into two components. One is along this direction, or tangent to the circle, and the other one is in the opposite directions of the tangent, right? Okay, so this is your theta here. So this force on this side, it is adjacent to the angle, so that's mg cosine theta. So you can see that your T, tension, and mg cosine theta, they should cancel each other because this ball is now moving in this direction. So tension and this force, the gravity component, they should cancel each other. And then there's this component, which is opposite of the angle. That force, we call that mg sine theta. That gives rise to the oscillation. So because of this force, it's going to do like this. So you can see that under the static the situation is going to oscillate back and forth, and the force is the force is not the whole gravity, is this component of gravity that does that. So there's up and like here that, and then the tension and this force, they cancel each other. So the gravitational force along this direction has nothing to do with the oscillation in this direction. Okay. So now let's see what keeps it rotating. So we can see that you basically have a ball that is rotating about this fixed axis, and there is a force. That force has magnitude mg sine theta. So when you have a force acting, that's acting at the distance away from the rotation axis, what does that force do? When you apply a force some distance away from the rotation axis, that force is going to produce something, but what thing? Huh? it's going to produce a torque, right? Do you remember when you have a force applied at some distance away from the rotating axis, that force is going to produce a torque, okay? So what is the magnitude of that torque? So that's a torque is equal to R cross F, right? So you have your R, you have your F, and let's say the R here is, let's say, the length of the string is L. So you have your R cross F, so you have your R, which is L, and then you have your force. Your force is mg sine theta, because only that force will apply to produce a torque. So you have your mg, and then sine theta. And then, what else? And you can see that the sine of the angle between them. This is L, the directions of the radius. This is the directions of force. So the angle between them is 90. Okay, so you have, so this is the force, and then so sine of 90. So it's just 1. So the magnitude of torque is equal to L mg sine theta. What about its direction? Is it positive or negative? So you have R cross F, so that's positive or negative. How do you do the R cross F? R cross F, so it's positive or negative? It is negative, so your torque is negative L mg sine theta. Okay, yes?
Is the force just like any, it's really like an external force that push it?
You mean this force? No, it's basically fall under its own gravity. So it's going to oscillate under its own gravity because you have the force, the component of that force, which is mg sine theta, that does that. So it will go from this point and then go back and forth, because it's in a dynamic equilibrium.
So the force is just the gravity force?
Yeah. Yeah. Yes.
How come there's that other force, like how come mg is not a force itself? Like that doesn't get canceled out by anything, so that's
For which force?
just mg is.
This mg has two components, right?
Oh, so that's not, it's not like there's mg and cosine theta.
No, I'm just saying that this is just the mg, and I'm just going to resolve the mg into this component and that component. And this component balance the tension, right?
Yeah.
Okay? And this component is not balanced. That's why it is actually moving. And because this force is applied at a distance from the rotation axis, so it produces a torque. And it is the torque that makes that keep it oscillating. That's basically what the pictures tells you. So we have a torque that has this magnitude, and it's actually basically doing the simple harmonic motion. So the torque is also equal to what? Torque is equal to R cross F. There's another expression for torque, which is, yes. Alpha, right? Exactly. So your torque is also equal to I alpha as well. So we have this expression. So let me just write it down again. So we have negative L, you have your mg, you have your sine theta, that's equal to I alpha. What we're going to do is that when you have a simple pendulum, your theta is usually considered to be small because you're not going to have oscillations like that. So for simple pendulum, the angle is pretty much less than 5 degrees, which is a linear motion. So if the angle is small, this is mathematically, this is one procedure that you can do. When theta is small, your sine theta can be approximated by theta. Okay, and we're going to utilize that. So what we have here is that you have your negative L mg instead of sine theta. Now we just have your theta that's equal to I alpha. And I'm going to also further, rearrange this. So I have my, let's see, how do I want to do it this way? Okay, so I'll have my alpha. So I'm going to so my alpha is equal to negative L mg over I and then theta. Why am I doing this? Because this thing is executed as a simple harmonic motion, and this is like an angular form of, not angular form, but it's basically, you have something that involves rotation. Angular acceleration, that's equal to this quantity times the angular displacement. Now that's the thing back for simple harmonic motion. When you have the acceleration as a function of time, that's equal to omega x of t, right? Okay, so if we compare this and this, basically, because it is always changing, which means that your acceleration, your angular displacement, they are function of time as well. This is what we did not write it down, but we can just write it here. Okay, so angular acceleration as a function of time is equal to this quantity times the angular displacement as a function of time. So this is for rotation. When you have a linear motion, that simple harmonic motion, you have the linear acceleration as a function of time that's equal to negative omega squared times the displacement as a function of time. You can see there's a one-on-one correspondence. So this is angular acceleration. This is linear acceleration. This is angular displacement. This is linear displacement. So we can immediately identify that, and they all have the negative sign. We can immediately identify that my omega squared is equal to this. And omega squared, so that's a frequency. For angular frequency, that will be like that, right? And so from this, we can actually deduce what the period is. Now, period itself has nothing to do with whether you have a linear or rotation motion. Period is just a quantity that's regardless the motion. So what we have here is that your omega is equal to 2 pi over t. This is my I. So what we have here is that my t, the period, is equal to what? Let's see, my t is equal to 2 pi and square root of is that I over mg? Mg, huh? Are we missing L? MGL, right?
Yeah.
Yeah, I think that will be because the length of the string is L. Yeah. So what we have here is that the period of simple harmonic,
Where's the x?
X? Now I'm just utilizing setting them equal to each other. Because I'm utilizing the fact that this is for angular, this is for linear, so there's a one-on-one correspondence. I'm not forgetting about x. I'm just going to say that, I identify this is equal to this. Because this and this, they are equivalent. One is for rotation, one is for linear motion. Okay? So what we have here, physicists are very lazy. Once they identify the pattern, they can just use it. They don't have to derive it. I mean, basically, you can derive the whole thing based on the physical principle. But then this is a shortcut. We identify there's a one-on-one correspondence. So once you know the pattern, you can just say that, okay, this must be equal to this. That's basically a shortcut and verified by a more elaborate derivation. Okay? So in other words, this is equal to this, so omega squared is equal to LMG over I, and then we know that omega is equal to 2 pi over t squared. So you square it, and then you rearrange that, you get your period. That's equal to 2 pi, and then times the square root of rotational inertia of that thing over the length of the string, the mass of the object, and then times g. Okay? So what does that give us? It just basically tells you, okay, how fast does it move? So it's just basically like that. We can actually utilize this. If you have just a simple arrangement like this, when you just have an object with a mass m that's located L distance away from the rotation axis, what will be the rotational inertia for that object? So let me just copy it down again. You have your t. That's equal to 2 pi, and then you have your square root of rotational inertia over L and then mg. My question to you is, what is my I here? What is my I? When you have an object, by definition, an object that's L distance away from the rotation axis, what is the rotational inertia? Yes?
Is it the mass and strength?
Exactly. That is as simple as that. It's just mass times the distance squared. So your I, for this arrangement, your I is equal to ml squared. So now we are ready to actually plug into this to see what we get. So your T is equal to 2 pi, and then you have your ml squared, you have your L, you have your mg. You can see that the mass of the object really doesn't matter because they cancel. And then you have your L, and then so what we have is just a simple expression, which is 2 pi, and then square root of L over G. Okay? So this is the period for a simple pendulum. It only depends on the length of the string and also depends on the free fall acceleration. And so you can see that this equation becomes very useful because it's so simple that you can actually use this to deduce the free fall acceleration by using this. Because when you have an object that just like, just doing this, you can actually measure the period. That's very easy to do. Just staring at it, provided you don't get hypnotized, then you get your periods, right? So you get your period, the length of the string, you can measure it. So then the rest will just plug into the equation and then calculate your free fall acceleration. So this is one way to infer the free fall acceleration. In fact, if you go to some big universities, they actually have that sort of device, like University of Cincinnati. If you just go to their physics department, they have, or some other physics department, they have several stories tall of the they have like in the center of the building, they have a big hallway, and then have the long string probably like several floors high, and then they have a big heavy object, and the thing just like slow. It's moving very slowly, and you can actually measure the time. Plug into this equation, and you can find out what the G value is. As we mentioned, the G value may not always be 9.8. It really depends on the geometrical locations and all that stuff. So this becomes a very useful way to infer the free fall acceleration or the gravitational acceleration. Okay. All right. So that is that. And in the book, it also mentioned the physical pendulum. So let me see. Do I want to do that? So physical pendulum. Basically, just modifications of that. The fundamental equation is up to this point. It works for any object because we haven't specified what kind of object that we have. If you have a physical pendulum, what does that mean, physical pendulum? Physical pendulum basically means that, okay, now you have an object that mass cannot be ignored. So now that's it, you have the object like this. The whole object is in rotation. And just go like this. So what will be the rotation inertia for this rod, for example? So you still have this equation still is the same, but when you're applying to a physical pendulum, that the size cannot be ignored. And if we have a rod, let's say we have a rod with a length of, let's say L, still L, and it's rotating about this, and let's say this rod is uniform. If it's uniform, what will be your rotation inertia? You have a rod, it's rotating about this axis, and this is a uniform rod. So where is the central mass? If it's a uniform rod, it's at the center, right? Okay, so do we know the rotation inertia about the central mass through when it's rotating about the central mass for a rod? Do we know that? Not 1/2? 1/12, exactly. It's 1/12, and then mass of the rod, and then the total length of the rod, right? So that is 1/12 ml squared. When you have a rod, that's rotation through the central mass. Is it rotating about the central mass? Where it is rotating about this location, right? So what is the rotation inertia then? What is our I? It's not ICOM. Parallel axis theorem. So you have ICOM, and then plus the the modification, right? How do we modify the rotation inertia? So M, and then what is the vertical separation between them? 1/2 L, right? Yeah, so is that correct? Mass of the object and then times the vertical separation between the two axes, because this is rotation through center mass. This is the actual rotation axis, so they differ by 1/2 L. The total length of the rod is L, so it's 1/2 L. All right, so when you add them together, what would you get? It's 1/2 ml squared and then plus 1/4 ml squared, and that gives you, do the math. Huh? 412, that'll give you 1/3, right? Yeah? Okay, so it's 1/3 ml squared. So so up to this point, it's very generalized. We haven't specified any rotation inertia. If we have a physical pendulum, and the physical pendulum has mass m with the length L, then it's uniform, then you can actually, so the rotation inertia is 1/3 ml squared. Then we're going to plug into this equation to see what t that we're getting. So you have your t, that's equal to 2 pi, and then your L is 1/3 ml squared on top. In the bottom, you have LmG. So again, you can see that your m just cancel, and your L, there's 1 here. So what we have here is that you have 2 pi and then square root of L over 3G. Okay? So basically, again, this,
What situation is this for?
this is when you have a physical pendulum, when this rod has a mass. Yeah, and then previously, this thing is, has a string. There's no mass. Only this has a mass m. Okay, so again, this is used. Am I doing it correctly? Yeah. So you square it when you. I think in the book you just square it and then rearrange that. So you square it. So this becomes 3, and then square it. That will be. That's only 4. Where does that 2 come from? 0.5. Substitute H. Oh, your H here. Your H here is 1/2 L. Let's see. With the uniform rod, H is from the center of mass. Let's see what we have here. Your L here. So it's basically the center. So it is actually the center of mass. So the it is half the L. So let's go back to this. So you have your I. We know that I is 1/3 m and then total length squared. Okay, and then your L here. Your L here is basically because you're rotating from all the mass will concentrate at the central mass. So your mass here is actually 1/2 L. So instead of using L, you will use 1/2 L. Okay, and then you have the mass, and then you have your G. So L cancel, and then you have that. So you have that will give you L on top, and you have your G in the bottom, and then you have your 3 here, and then you have your 2 here. Okay, and then after you square it, then so basically in the book, after you square it, rearrange that, you can find that your G value is equal to 8 pi square the length of the physical pendulum, and then over 3t squared. Okay, so again, that just illustrates that you can use this kind of device to infer the free fall acceleration because all this quantity are fixed pretty much. Your L, the length of the physical pendulum can be measured, and the time you can just do numerous measurements, and then just plug into this equation. Then you can figure out what the G value is. We can actually do this experiment, devise an experiment, and then just find the G value quickly, and then compare it to the 9.8. Yes.
How will that equation is still the entire length of the rod, not like L divided by 2, right?
Which one?
The one you just boxed out, right?
Yeah, that will be the entire rod, but it's actually because it is actually the central mass that is in rotation. So instead of accounting for the whole length, you would really have to actually just utilize that as if the whole mass is actually concentrated at that point. That's the whole idea of because it's extending object. So instead of using the end point, you will have to use the central mass. Okay? Yeah? Which one? This one? There's a 2 pi here. So period is equal to 2 pi and then this. And then,
Isn't it equal to G? I'm sorry, like that.
so after you square this, square that, rearrange that, then your G is equal to this.
Is G always equal to that, or only in this case?
Only in this case scenario, because this is like I said, this equation is generalized form. And we apply to simple pendulum, that gives you this expression. We apply to a physical pendulum, and that gives you that expression. So it really depends on the case. This is more generalized. This we did not specify what the rotation inertia is. Okay, it depends on what kind of object that you work with. Okay. Yes.
Sorry, just to clarify. So
Uh huh.
L isn't always going to be pi 1. It's going to be from the village to the center of mass.
Your L is from the rotation axis to the central mass. Yeah. So yes. So this L here, to be that will be from the rotation axis to the central mass. When you just have a simple pendulum, the mass is located here. So this is where the central mass is. If you want to look at that way. When you have a pendulum, when you have a physical pendulum, the mass is uniformly distributed along the entire rod. So the central mass will be the one to find the rotation inertia. Okay? All right. So that concludes. I mean, in this book they also describe, when you have simple harmonic motion, it does not oscillate forever. In fact, it actually, after several oscillations, it comes to a stop, and that is because there's a friction. When there's a friction, there's always take away energy. And when you have a friction, this is in a case very similar to the drag force. If you remember, the drag force is proportional to the velocity. The faster the object moves, the larger the drag force in order to slow it down. So for simple harmonic motion, we have very similar situation. So when you have simple harmonic motion that's that's oscillating, and if there's a frictional force, that frictional force is proportional to how fast the simple harmonic motion moves. So if the oscillator moves faster, then the friction force is also faster as well. So in such a way that to slow it down much faster. Okay, so mathematically you can derive the solution to is the second order differential equation. You can actually find out the solution and blah blah blah. So we're not going to do that in this class. Okay, and so basically that concludes this chapter.